Developing news tonight, a severe geomagnetic storm has hit Earth, actually the strongest in nearly 20 years, and it comes with the warning that communications and the power grid could take hits this weekend.
In recent days, scientists have been closely monitoring Sunspot AR3664, which has been lingering on the surface of the sun without dissipating. Researchers have made it a focal point of study because this sunspot appears to be the largest and quite active. Such sunspots can also impact Earth's weather, and if a solar storm were to erupt from this sunspot and head towards Earth, the consequences could be significant. You can't even imagine the impact such an event could have on our planet. In this video, we delve deep into this phenomenon to provide you with startling information. Failure to mitigate such storms poses the biggest threat. We'll draw parallels to historical solar events like the Carrington Event of 1859 to underscore the significance. Have events similar to Carrington occurred today? Why is it a danger for us? You're watching the Cosmic Discovery YouTube channel. Sunspot AR3664 isn't your ordinary spot on the sun. It's a colossal one, among the largest and liveliest sunspots we've observed during this solar cycle. Spanning nearly 200,000 kilometers, this sunspot dwarfs our planet, being over 15 times wider. Its immense size means you can even spot it with simple eclipse glasses, making it a favorite for educational programs aiming to ignite curiosity about solar physics and space weather. This activity with sunspots perfectly illustrates how they affect solar phenomena. Sunspots are temporary spots on the sun's surface that are darker than the surrounding area. They are areas of low surface temperature due to concentrations of magnetic flux that prevent convection. Sunspots appear within active regions, usually in pairs of opposite magnetic polarity. Sometimes, these magnetic fields become entangled and strained, resulting in a sudden burst of energy called a solar flare. AR3664 has been incredibly active, unleashing numerous M-class and even X-class solar flares. Solar flares are intense bursts of energy. According to NASA, these fiery outbursts and solar eruptions could interfere with radio signals, the power grid, and navigation systems, posing risks to spacecraft and astronauts. Moreover, this sunspot has also been linked to several coronal mass ejections, CMEs. These breathtaking solar events occur when massive bubbles of gas and magnetic fields erupt from the sun's corona. Depending on their trajectory in space, CMEs may intersect with Earth's magnetic field, triggering geomagnetic storms capable of disrupting power grids and satellites. The recent surge in activity from this sunspot serves as a stark reminder of the sun's significant impact on our modern technology. This capacity for disruption underscores the critical need for continuous monitoring of these sunspots. Yuck occurrences carry the potential to jeopardize Earth's systems, which is why scientists are diligently seeking ways to mitigate their effects. To closely monitor these phenomena, scientists employ an array of tools, including space-based observatories like NASA's Solar Dynamics Observatory and ground-based solar telescopes. Through analyzing the development, movement, and magnetic characteristics of this sunspot, scientists gain valuable insights into the mechanisms behind solar flares and coronal mass ejections, CMEs. Data gathered from these solar storms aids researchers in studying and forecasting space weather. This understanding is crucial for enhancing predictions of space weather events, thereby safeguarding satellites, power grids, and other vital infrastructure from the unpredictable nature of the sun. Observatories and science centers worldwide are seizing this unique opportunity to educate people about the dynamic nature of the sun and its implications for Earth. Using projected images on sidewalks or screens, even those without a telescope can witness the rotation and evolution of this particular sunspot over several days. As we near the peak of the sun's 11-year activity cycle, the knowledge gained from monitoring this sunspot becomes increasingly vital. Observing and studying it highlights the significance of celestial phenomena and their profound influence on our technology-driven world. The Carrington Event stands as the most powerful geomagnetic storm ever recorded, reaching its peak on 1–2 September 1859 during solar cycle 10. Named after astronomer Richard Carrington, This event remains unparalleled in recorded history for its intensity. It created strong auroral displays that were reported globally and caused sparking and even fires in several telegraph stations. The geomagnetic storm was likely the result of a coronal mass ejection, CME, from the Sun hitting the Earth's magnetosphere. The geomagnetic storm was associated with a very bright solar flare on the 1st September 1859. It was independently observed and recorded by British astronomers Richard Christopher Carrington and Richard Hodgson, the first record of a solar flare. Researchers believe that if a geomagnetic storm of this magnitude occurred today, it would cause widespread electrical disruption. Blackouts and extended outages of the electrical power grid will cause damage. Emerging from a colossal solar flare interacting with Earth's magnetic field, the significance of this historical occurrence in shaping our contemporary comprehension of solar phenomena cannot be overstated, particularly as we witness the actions of sunspots like AR3664. The parallels drawn between the Carrington Event and the recent behavior of this sunspot serve as a vivid reminder of the sun's capacity to disturb Earth's technological infrastructure. Within a mere 18 hours of the flare's occurrence, now famously known as the Carrington Event, the ensuing geomagnetic storm had already reached Earth, underscoring the rapidity and potency of solar ejections. Telegraph networks spanning Europe and North America faltered, as operators witnessed sparks flying from their equipment, some even igniting fires. Fast forward to today, AR3664 mirrors this historical giant, exhibiting vigorous flares and coronal mass ejections, CMEs, capable of inducing comparable, if not more severe, disruptions to our technologically dependent world, given our heightened reliance on electronic systems and satellites. Following the Carrington Event, auroras typically confined to polar regions were observed as far south as Cuba and as far north as Queensland, Australia, vividly illustrating the immense geomagnetic forces in action. Given the recent surge in activity from AR3664, scientists and researchers have intensified their vigilance, understanding that these dazzling auroral displays signal significant shifts in Earth's magnetic field, which could foretell more widespread electronic disruptions. The cultural and scientific impact of the Carrington Event still echoes today, serving as a reference point for understanding contemporary solar phenomena. Conversations surrounding AR3664 in both academic and public arenas raise various concerns, with the possibility of internet shutdowns or widespread power outages often taking center stage. Our modern infrastructure, intricately calibrated and heavily reliant on stable magnetic conditions, remains susceptible to solar storms akin to those witnessed in 1859. The measures implemented after the Carrington Event, such as reinforcing electrical grids and shielding satellites, demonstrate continual endeavors to reduce these susceptibilities. Looking ahead, the insights gained from monitoring this sunspot are incorporated into worldwide readiness strategies. Organizations like the United Nations Office for Outer Space Affairs and the International Space Weather Initiative are dedicated to improving collaborative resources essential for forecasting and minimizing the effects of space weather. Picture a contemporary version of the Carrington Event. Its repercussions would extend well beyond captivating auroras, potentially dealing a severe blow to the global economy and upsetting everyday routines. This scenario isn't merely a speculative concern, it looms as a genuine threat as Sunspot AR3664 persists in mirroring the behavior observed in 1859. Considering our heightened reliance on technology, the scale and impact of a Carrington-like event today could surpass any previous experience, amplifying its potential consequences. At the time of the original Carrington Event, humanity was just starting to embrace electricity. Telegraph systems represented the most sophisticated electrical technology in widespread use. In today's world, we're surrounded by a network of GPS satellites, power grids, and fiber optic cables. If a severe solar storm were to strike now, the consequences could be widespread. Satellite communications might go offline, GPS navigation could become unreliable, and power grids, crucial to modern life, might fail on a regional or even global scale. The economic repercussions of such an event could be significant. Research conducted by the National Academy of Sciences highlighted potential economic losses to the North American economy reaching trillions of dollars, with recovery periods stretching over years. Apart from financial impacts, there are also human and environmental concerns to take into account. Vital systems such as hospital equipment and water purification processes heavily depend on reliable power sources. An extended blackout could jeopardize essential services ranging from healthcare to access to clean drinking water. Despite these grim forecasts, progress since the 19th century has equipped us better to confront such threats. Present-day scientists employ advanced models to forecast solar activity and its potential repercussions. Agencies like NASA and NOAA manage fleets of observation satellites, furnishing vital real-time data essential for early warning systems. On the international front, policies and protocols are being formulated to address severe space weather events. Drills simulating large-scale solar storms are conducted to assess the resilience of both national and global infrastructure. These endeavors are pivotal in constructing a response framework aimed at mitigating the havoc wrought by a Carrington-level event. Lastly, as AR3664 underscores the formidable might of our Sun, it highlights the critical need for adaptability and ingenuity in safeguarding our interconnected world. Observing and studying AR3664 not only deepens our understanding of solar physics but also underscores our susceptibility to the immense forces of our solar system. Through unwavering vigilance and scientific inquiry, we strive to ensure that even in the face of potential repetition of history, we are more prepared than ever to confront its challenges. Solar storms, also known as space weather events, have the potential to cause a wide range of damages and disruptions. These storms are primarily driven by intense activity on the sun's surface, particularly from phenomena like solar flares and coronal mass ejections, CMEs. 1. Disruption of communication systems. Solar storms can interfere with radio signals, satellite communications, and GPS navigation systems. This interference occurs due to disturbances in the Earth's ionosphere caused by the influx of charged particles from the sun during solar flares and CMEs. This disruption can affect various sectors, including aviation, maritime, and telecommunications. 2. Power grid failures. Geomagnetic storms resulting from solar activity can induce electric currents in power grids, leading to transformer overheating and equipment damage. This phenomenon can cause widespread power outages, potentially affecting millions of people and disrupting essential services such as healthcare, transportation, and emergency response systems. 3. Satellite damage. Solar storms can damage satellites in orbit around the Earth. The energetic particles and increased radiation levels can degrade satellite electronics and solar panels, leading to malfunctions or complete failure of critical satellite systems. This can impact services reliant on satellite technology, such as weather forecasting, navigation, and global communications networks. 4. Auroral displays. While not directly harmful, intense solar activity can produce spectacular auroras, also known as the northern and southern lights. While beautiful to observe, these auroras are a visible manifestation of the increased energy in the Earth's atmosphere during geomagnetic storms, indicating the potential for more severe impacts on technological infrastructure. 5. Health risks. High levels of solar radiation during solar storms can pose health risks to astronauts and airline passengers flying at high altitudes. Increased radiation exposure can lead to radiation sickness, DNA damage, and an elevated risk of cancer. Astronauts aboard the International Space Station, ISS, are particularly vulnerable during intense solar events and may need to take shelter in shielded areas to mitigate radiation exposure. Overall, solar storms have the potential to disrupt modern technological systems and infrastructure, highlighting the importance of space weather monitoring and preparedness efforts to mitigate their impacts on society. As we conclude our exploration of the captivating world of solar storms and their potential impacts, remember to stay informed and prepared for any space weather events. Subscribe to our channel for more fascinating insights into astronomy, space exploration, and the wonders of the cosmos. Don't forget to like and share this video to spread awareness about the importance of understanding solar phenomena. Until next time, keep looking up at the stars.